All right, so here we go. We're going to roll into working with contingency tables, but I wanted to start with a couple of, and maybe I have 3 of these. No, I got 2 questions that are related to two-way tables. So Ms. Tucker travels through 2 intersections with traffic lights. Once again, we have 2. So a table is not exactly a sample space, but it's pretty close. And so once again, you're doing something twice, or you have 2 variables, table or a sample space. The traffic lights operate independently. That's going to be important later on. I'm just going to let you know that. The probability that both lights will be red when she reaches them is 0.22. The probability the first light will be red and the second light will not be red is 0.33. What's the probability the second light will be red when she reaches it? So I'll see this and I go, gosh, that's a lot of information, and I need an organizational tool to organize it. So my organizational tool is my table, and I'm going to call this light 1. Over here is light 2. This is red, and this is not red. This is red, and this is not red. All right, so the probability that both lights will be red when she reaches them is 0.22. Well, that's red and that's red, so that's 0.22. That's easy. The probability the first light will be red and the second light will not be red is 0.3. Well, we said this was light 1 and not red, so light 1 is red, second one not red is 0.33. So that means the probability right here is just 0.55 because I can sum those up directly. But now I'm stuck, or at least I think I am, because I don't have any more information. They didn't give me any other work to work with, except they told me that it was independent. And remember, oh, and they said, what is the probability the second light will be red when she reaches it? So we're interested in this light, this value right here. We want this value right there. Second light's red. Well, remember the probability of A times the probability of B equals the intersection if they're independent. Well, we know that this is 0.55. We know the intersection is 0.22. I just don't know B. And if I take 0.22 and divide it by 0.55, I end up getting 0.4. So that value is 0.4. And if I multiply this times this, I get that value. But it's a little bit tricky because you have to remember the independence rule and you have to be able to fill out part of the table. All right, this next multiple choice problem is, I think, one of the more difficult ones that show up. So for flights from a particular airport in January, there are 30% chance of a flight being delayed because of icy weather. So here we're working, and by the way, when we're working with tables, we're trying to find the single variables. If we have a number associated with a singular variable, we can place it. But if it's associated with 2 variables, we can't. So there's a 30% chance of a flight being delayed because of icy weather. If a flight is delayed because of icy weather, there's a 10% chance that it will be delayed because of a mechanical problems. So here we have 2 different things. If a flight is not delayed because of icy weather, there's a 5% chance that it will not be delayed. So another thing is we have 2 variables here. So the one associated with only one thing variable is here, because we have flight delayed and weather mechanical delay. We have mechanical delays and ice delay. And here there's a 30% chance because of icy weather. So that is my starting point, because it's only that number is only associated with one variable. So with that being the case, 30% is going to go right here. This is going to be 0.70. This is, of course, one whole. ice delay, no ice delay. The other type of delay was a mechanical delay. Mechanical delay, no mechanical delay. So now I'm going to take this number and bring it up small, 0.30, 0.30, 0.70, 0.70. So if a flight is delayed because of icy weather, so I'm looking at the icy column, there's a 10% chance it'll be delayed because of mechanical. Oh, so this means this is a 10%. And this has to be the complement of that, a 1 minus 0.9. So let's go ahead and multiply those real quickly. I don't trust myself tonight. So 0.03. And this is 0.27. The next thing is if a flight is not delayed because of icy weather, there's a 5% chance it will be delayed because of mechanical. Okay, not ice, but there's a mechanical chance of 0.05. So this ends up being 0.035. And this ends up being 1 minus 0.05 or 0.95. So 0.665. All right. I sum these up and I get this to be 0.065. And this is 0.935. All right, so what is the probability that it will have at least one of the two types of delays? So what's the probability to have an ice delay or a mechanical delay? Now, I just said something really important. I said or. That means probability of A union B equals the probability of A plus the probability of B minus the intersection. So the probability of an ice delay is 0.30. The probability of a mechanical delay is 0.065. But I have to subtract out the intersection because that part got counted twice, just like it got circled twice, minus 0.03. So 0.3 plus 0.065 minus 0.03 is 0.335, and that gives me the answer to that problem. And that's a fairly challenging problem because not only did you have to set up the table, but you had to remember the probability of A union B equals A plus B minus the intersection. Now that formula is on the formula chart, but you have to still remember to use it. All right, so here's our FRQ on tables. Approximately 3.5% of all children born in a certain region are from multiple births. Oh, gosh. That looks like that's associated with a single variable. Of the children born in the region who are from multiple births, 22% are left-handed. 22%, that's from the group. That's conditioned because it says if from the group given, those are conditional words. That means that's two variables. Of the children born in the region who are from single births, once again, it's conditioned, are from single births, 11% are left-handed. That one is also conditioned, so it's also two variables. So our one variable is just 3.5%. So what is the probability a randomly selected child born in the region is left-handed? Well, we know we have a lot. We have three things. Anytime you have three, it's almost always a table when it comes to percents. So if I go to look at that, this is going to be 0.035. This is 1 minus that, so 0.965. And that's one whole. And multiple births, single birth. And then the left-handed, right-handed, or not left-handed, however you want to look at it. So I'm going to bring this up in small numbers, 0.035 and 0.035, 0.965, and 0.965. What's the probability of randomly selected child born in the region? Oh, so of the children who are from multiple births, so from multiple births, 22% are left-handed. So that means this is going to be 0.22, and this is 1 minus 0.22. Of the children born in the region who are from single births, 11% are left-handed. So this is 0.11, and this is 1 minus 0.11. And that'll get us to our table, and we can multiply that out. And to speed things up, I'm going to go ahead and flip over to everything's been multiplied out. So it says, what's the probability a randomly selected child born in the region is left-handed? Well, left-handed would be that row, which is 0.11385, after we multiplied everything out. And remember, this plus this will equal that. Next part, what's the probability a randomly selected child born in a region is a child from multiple births, given the child is left-handed? Oh, so that's going to be intersection over given. We're given that they're left-handed. And what's the probability of their multiple births? So the part that got circled twice is my intersection. So this was my numerator, and that's what we were given. So that's my denominator. And by the way, once you have the table set up, if you just gave this as your answer and gave that as your answer, that's fine. I like to convert it into decimals. So this equal that, but if you just had the fraction, that'll work. You do have to have the fraction right here, but you don't have to have all the labels. Finally, a random sample of 20 children born in the region will be selected. What's the probability that the sample will have at least 3 children who are left-handed? Oh, wow. So we have a probability of being left-handed. That's the probability of left-handed. That's a fixed probability, and we have a fixed number of trials. This tells me I'm working with a binomial. So 0, 1, 2, 3, all the way to 20. So this is what I'm looking for, is this group right here. So there's a couple ways to show this. 20 choose 3. There's my probability, 1 minus that. 20 minus 3 is 17, and then 20 choose 20. And that work will work great. Alternatively, you could do 1 minus 20 choose 3. I'm going to shorten this up because it's got something I have to write this part out. Oh, excuse me, 20 choose 0, excuse me, 20 choose 0 plus dot plus. We take the highest thing we don't want, which would be 20 choose 2, because I'm going to have to include this part as well on that. But that would take care of showing the work for the binomial. And then we just plug it into the calculator as a binomial CDF. Trials is 20, probability is this, and we're subtracting out 2. We're always subtracting out the smallest value, and the largest value that we don't want. And we want 3, so we don't subtract it out. We don't want 2, so that's what we subtract out.